If you place an opaque object in front of a light source, geometrical optics tells us the resulting shadow should have a razor-sharp edge. Light travels in perfectly straight lines, so the boundary between light and dark should be absolute. Look extremely closely at the edge of a shadow cast by a sharp object, and that absolute boundary falls apart. The edge is blurry. It consists of faint alternating dark and bright bands. You see this same optical anomaly when you look at the surface of a compact disc. The shimmering colors visible across the disc are produced by light bending and interfering with itself as it bounces off the microscopic grooves. In the 17th century, Isaac Newton championed the corpuscular model of light, arguing that light consisted of rigid particles traveling in straight lines. But this model could not explain those blurry shadow edges or scattered colors. The physical concept driving these anomalies is diffraction. Diffraction is the general characteristic of waves to spread out and bend around obstacles or squeeze through narrow openings. We rarely notice this bending in our daily lives because the wavelength of visible light is vanishingly small. The wavelength of yellow light, for instance, is only about 0.6 micrometers. To map the physical universe accurately, we have to let go of the perfectly straight line. Those fuzzy shadow edges prove that light behaves as a restless, spreading wave. We can isolate this wave behavior in a classic physics setup. We take a parallel beam of monochromatic light, which is light consisting of a single uniform wavelength, and force it to pass through one incredibly narrow microscopic slit. Instead of shooting straight through the gap, the light hits the opening and balloons outward into regions of pure shadow. This is Huygens' principle. If you imagine the slit divided into smaller parts, each part acts as a fresh source, generating new, spreading secondary wavelets. This diagram shows light energy is never lost or destroyed. It is simply redistributed by wave interference, taking energy from the dark fringes and stacking it into the bright ones. This principle extends far beyond laboratory slits. We rely on circular openings to observe the world every day, from the pupil of the human eye to the lens of a microscope or the aperture of a telescope. Because these instruments use circular openings, every single point of light that enters them is forced to diffract. The light spreads out into a central disk and faint rings before it ever hits our retina or a camera sensor. This creates a high-stakes scenario when we try to observe two incredibly close objects, like two adjacent microscopic cells or a distant binary star system. As magnification pushes these points closer together, a visual collision occurs. Their individual diffracted waves begin to overlap. Eventually, they merge into a single blurry blob. At this exact moment, it becomes physically impossible to tell if you're looking at one object or two. This unbreakable physical barrier is known as the limit of resolution. This limit is not an engineering flaw. It cannot be fixed with perfectly polished glass or larger mirrors. It is a hard-coded law of physics, dictated entirely by the wavelength of the light itself. The fuzzy edge of a shadow and the blurry limit of a billion-dollar telescope are the exact same phenomenon. They are a permanent reminder that we exist in a universe governed by the restless, inescapable geometry of waves.